you will be talking from Dubai through this magic called technology. Please.
Thank you, Ricardo. And yeah, thank you everyone for coming along and attending and bearing with me through the cyberspace. It's always better to do this stuff in person. But yeah, part of where we're moving in terms of collaboration and using digital is to be able to do this sort of thing remotely. So I think it is a good test. Now, yeah, and thank you for the introduction, Ricardo. I might just elaborate a bit on that by explaining how I became involved with the Smart Infrastructure Facility. I've been working with Juan Castillo there. He and I have shared a similar view on how digital transformation can really impact these environmental management challenges. So we've been working on using the same technology and the same business process together to solve some of these complex multi-stakeholder water resources focused problems. So he's been working a lot in groundwater. I've been working a lot in groundwater, nutrient runoff, and the use case we'll go through today is flooding. So I'll check, can you guys all hear me and see me properly? Is the setup all correct? Yep. All right, so let's just get stuck straight into it. I'll try and share my screen instead of being a big fat head on the wall. Okay, so first I want to break down a bit about the title of the talk. These words mean something. They're not just buzzwords. The component of user-focused, what we're talking about here, when we're using digital collaboration and online, people tend to have a shorter attention span than if they're physically in your office coming down and looking at a PDF report. And they have the ability to turn on and off their engagement with you by opening or closing the browser. This is something that a lot of the consumer marketing and consumer-facing apps like Facebook or LinkedIn or any of these guys will tell you very quickly. When you're working through the web, you have to be really providing value, user-focused content all the time. So when we're interacting with each other and with our projects through the web, it has to be valuable, and we can't have room for repetitive tasks and problematic user experience. So that's really important for me. The digital collaboration bit, as we're dealing with environmental style problems, and everything I'll talk about today is based around solving problems that have many stakeholders and a wide geographical distribution. So I'm going to use the example of flooding to talk through the processes that we've been exploring. But honestly, this can work with traffic, it can work with water quality, it can work with groundwater, it can work with bushfire management. Basically, any situation where you have many different stakeholders and different use cases as well. Each stakeholder will take a different perspective on what they want from a flood model or from a bushfire model or from a traffic model. So in this kind of environment, traditional collaboration can be a challenge. The face-to-face bit is always super important to go around and meet the people that you're working with. But as the project evolves and changes, it becomes increasingly challenging to go around and meet with all 20 stakeholders twice a week to keep them all up to date. And this is the problem that digital is solving for us. It's providing online platforms where each stakeholder and each collaborator can go in and get the information they need from a single spot quickly and easily. And the resilient cities part of the title, the end result and the reason why we're doing this is to provide management frameworks for our cities that can evolve with time and evolve quickly and easily. We're trying to move away from the concept of having a flood study or a traffic study or a bushfire study as a static point-in-time snapshot that only gets updated every 5 years. And we're trying to move to a continuous improvement process that allows our cities to evolve as change happens rather than in stepwise funding-driven, government cycle-driven processes. So that's a bit of a breakdown about the title. And I'll move in now to talking about how we actually go about making this a reality. So the case study here I'm going to use is one that was built by Wollongong Council. Peter Malevsky put together this model of Tauraji in the Anuga hydraulic modelling software. The benefit in this case of using Anuga, and the reason that we've been drawn to it as a prototyping piece of code, I guess, to put together this business process, is that it's open source, and that means we can scale it and share it and build a community in a way that's just not possible with some of the proprietary codes. And this has proven really effective in driving transparency around the engineering decisions that we're making, and in keeping all those design decisions that go into a process open, transparent, and consistent. Okay, you have to bear with my internet connection. I think I'm streaming a bunch of stuff through a VPN, so it's a little slower than I'd normally have. So what I want to do to start with is talk you through the basics of the information that goes into a flood model. And from this point, the guys that are familiar with flooding and focused on flooding, it'll be second nature to you. But for those who might be focused on other urban challenges, I want you to look at the way we've set up the data and focus on the different data sources that we're using, and see how they'd fit into your water quality or your traffic or your bushfire study. So basically the first step in getting these models online is to build all the data together in one spot. Now, for a flood model, that starts with having terrain data. And so here we've imported the digital terrain model for the whole area. Now, on top of that, we define some model extents, which is this red line here. That's the calculation boundary that we're going to use for the model. And then on top of that, we need some driving forces, which in the case of a flood model is rainfall data. So this is each one of these polygons represents rainfall falling on this particular area of the catchment, and you can see here in the database we've stored a hyetograph that will be applied to the model when we run it. So that's the basics of how flood model works and what we're trying to do. Now, when we actually run this thing, you guys have probably all seen some kind of result like this, but you'll be used to seeing it in a PDF report or perhaps as static GIS layers that are provided by a consultant and then built into a communal GIS system. But what we've done here is moved everything up into the cloud, and we're running it all straight through the browser. I'll talk a bit about how we do that in a minute, but for now you can see this is mapping the water flow and the depth of water throughout the area and highlighting areas where we might have a problem. I know the guys from Wollongong Council are there. This model hasn't been calibrated, so please don't get too fussy about the actual depths. I haven't got all Peter's calibration in here yet. And then it's not just the water depth that we're calculating. We can also look at other hydraulic factors. For example, the velocity here often tells us a lot about what's going on. You can see the water's flowing faster down the streets than it is through the properties. That's because we have applied different values of roughness to the surface here to produce different reactions. Water flowing through the back of the houses is going to flow differently to the water flowing through the streets. So here you can see the roughness map that we've applied across the whole model. So that's just a basic overview of, well, one, what a flood study is, and two, how it looks when we move all that data up online. So I want to talk a little bit about what is the business problem that this is solving, and why would we go to all this effort of pulling it all up online and running it digitally. In a traditional study, it's typically stored in a PDF report or static GIS layers. A little bit of hard copy. I guess there's not too much of that going on these days. But the challenge that we're trying to solve is, once this study is finished and either the consultant or the in-house engineer who's done all the great technical work to capture all this data and build a flood study, once they've signed off on their contract or left the organisation, it's really difficult to update these studies. It's hard to manage change as the catchment, the watershed evolves, and often this can involve in needing to re-engage the consultant simply to update it. And in the case of a council flood study in New South Wales, it can mean going back to council and getting the flood study reapproved at a council meeting. Essentially, the challenge that we're looking at is, when you're investing in these studies, they depreciate in value. As soon as you finish the contract, the thing starts losing value. In the same way, the best analogy I've come across is that of a car. Once you buy a car, the value of the car starts going down from the day you drive it out of the shop. So using online, we're looking at a different strategy to how we manage that data and how we manage the value that we've put into these studies. By storing it online, either in the public or private cloud, there's a bunch of different ways you can do it. Essentially, the key feature is that we can update and edit it online, and we're not losing all that brilliant work that's gone into the study every time someone new comes on and every time some new information becomes available. So essentially, we create a study that can appreciate in value and get better with time as we use it more, and as we collect more data, we're continuously updating these things. And it's like investing in a house. Sure, the real estate market's going up and you're getting more and more value from it, but at the same time, you do still need to maintain and put new investment into the study. But the point is, the thing's going up rather than down, and you're getting a better return on investment. So now I want to run through a bit of an example of how this might actually play out in real life. So I'm going to flick a little north of Sydney now to an example in Merewether. This particular data set's one that's been used by many flood models and flood engineers to calibrate and build example models. So it's a good one for us to work through. But this process can occur basically anywhere on the planet. I can zoom out from this map, and you're in a continuous modeling environment that can scale and apply anywhere on the planet. So what we've got here is a digital terrain model that we've uploaded in Merewether, and then on top of that, our consultants say we're now working for the council, and our job is to regulate development within this flood study area. Our consultants have provided us with the all this data, the houses, and the different bits and pieces that I showed you about the flood study. The first thing we want to do is actually apply an inflow into this model. So to be correct, this is probably what the consultant will still be doing. I'm going to call this inflow, say, the 100 year. And at that line that I've just drawn, I'm going to apply a hydrograph that I've already stored in there. I've skipped over a few steps because in half an hour you probably don't want to watch me build an entire model. But on this line that I've drawn here, I've applied a hydrograph, as you can see, that's basically represents the 100-year flow through this section. Now, the next thing I'm going to do is create a scenario and actually run the model. So I'm going to select the elevation model that we've put in, the model boundary, use the existing houses that we have here, apply that 100-year surface inflow that I just showed you, skip over the friction and the vertical walls for this. I'm going to run the resolution at 5 meters, save results every 60 seconds and run it for a total of 20 minutes in real time. So you get an idea here how you can create different scenarios and test different results directly in the browser. And throughout that whole process, I didn't have to go onto my hard drive and go and find the terrain model file called Dave's model, or work through any file naming conventions, or deal with any of the typical challenges that a numeric modeler spends a lot of time doing every day. So by putting this stuff in online and automating a lot of those processes, we can control all that user experience for the modeler and for the user a lot better. And this means that engineers can actually focus on doing engineering rather than data management, and the decision makers can focus on testing decisions and building the scenarios rather than actually having to deal with the back end of the model. Having said that, every time we do run a model here, we're saving all this data into a normal zip file, a traditional file structure, and you can download that and view it and run it as a standalone package for every simulation that you run through a platform like this on your computer. And of course, because it's open source, you can download any of these models and run them straight on your desktop as well. But we're running this as the simulation finishes. We're running it straight on the Amazon cloud, and this gives us a few advantages over running on your desktop. For example, I think the server that we just ran this model on is running 96 CPUs, 96 cores. So the model will run an awful lot faster in the cloud than it would on your 4-core or 8-core modeling computer that many engineers might have as a desktop. The other advantage of storing each model run as a standalone package in a zip file is that it provides a history of who ran the model with which data set at what point in time. And that really goes a long way to building a history of the model and building a defensible and understandable reason for all the model runs that have gone on. Often the responsibility for this is put onto the consultant or the modeler to build and manage their own model log runs. And there's a bit of inconsistency in how different modelers would manage that kind of data. So here you can see the results of that simulation I just ran. There's the line that I just drew with where we put the flow in down the bottom of this catchment, and then the water's flowing through the houses here and out the top of the model here. You can see the terrain model is effectively replicating shallower water through the crest of the road and deeper water along the gutters. And there's some build-up of depth behind the buildings there as well. So what we've focused on here is doing a really user-friendly and simple modeling platform that has all the same power and strength of working with the actual source code, but making it very focused on getting results quickly and easily. And of course, I can query this kind of data and get the specifics around the velocity or the depth. Okay, now from here, we're going to take on the role of working as a regulator to assess a development application that someone has put in to extend this particular property we're going to build a granny flat out the back. So let's load up the proposed model. And what I'm going to do is edit this data to edit the geometry here to replicate what might be the first pass building footprint that the developer has proposed for this particular site. So in this case, that's a bit taking too much footprint away from them there. There's the granny flat, the extension that they're proposing. Now, of course, when they're developing it, they might not realize that they're putting it straight through an overland flow path here, because they traditionally wouldn't have access to this kind of online data. And so although we might be able to see that that's not the best spot to put a granny flat right now, our developer has come into our office and said, look, this is what I want to build. So now, as regulators, we can, let's call this one the proposed scenario and load in those proposed houses that we've just created. And we'll keep all the other settings exactly the same. Now I've got this new scenario here. I'm going to go ahead and run this model. And now for the sake of time, I'm going to skip ahead and run the second model at the same time before I wait for the results on that one, because I can kind of tell what's going to happen. And I'm going to create a new scenario as well where we're mitigating the impacts of that particular model. That particular proposal, and coming up with something that might be a little more hydraulically acceptable, whereby we're moving the building footprint out of the flow path here. I'm going to knock down this shed to provide a bit more space, so I'll delete that feature. And because we're still impacting on the flow path here a little bit, in this particular case, we're going to move redesign this existing building a little bit too. Now, look, maybe that's probably not the architectural reality of life, but for demonstration purposes, I'm just trying to create a bunch of scenarios here so we can compare the results later on. And now that we've put together those mitigation measures, we can do the same thing and create a new scenario around how we might actually mitigate the impact that the developer's original proposal would have had on our flood regime. So the whole point of what we're trying to do here, I'll just run that one, is provide really quick feedback early on in the development process so that people don't invest too much time and energy and money in developing their proposal to a point where it's difficult to change. And we're trying to grow the flood study in a way that's going to evolve over time as every one of these development changes goes on throughout the catchment across your entire watershed. By continuously updating and rerunning the model in this fashion, we're looking to really evolve the city in a way that is cognizant of the flood risk for every project, and it avoids that problem where you have death by 1,000 paper cuts, right? So I'm gonna just let that one run through. We'll flick back to the slideshow. While that's running, I want to talk a little bit about how we can actually make this work and how we can move online. Now, in this space, I'm talking not just about the flood models, although this is the methodology that we've used to create this platform. It doesn't matter which problem you're trying to solve. When we're moving data online, the first step is to build a common data environment. And the purpose of doing this is to create that single point of truth. For a flood study, that means mixing the cadastral terrain, transport population data for evacuation routes. But the similar philosophy applies whether you're building information modeling using BIM technology like Bentley's ProjectWise, or even collaborating on a report using Office 365. The basic idea is to get all your data up on the line into a database so that everyone's working off a single point of truth. Some interesting examples of this. Facebook is a great example where a lot of users only really see step one as what's going on, which is basically getting all your data up online into Facebook. Facebook themselves are running behind the scenes what I'll call step two, which is where they're using that data and calculating things and building stuff off it. But from the user implementation, this is where Facebook sits. A really relevant example for this level is the New South Wales SES flood database, which I know some of you guys have been involved with. That's built using the CCAN technology, which is an open source technology. It's essentially a document store for geospatial files. There's a sister project out there for CCAN called GeoNode, which is essentially a geospatial version of CCAN. And that's what we're using here to wrap around the Yanuga model. And we use GeoNode essentially as a content management system to store all our data, get it online. The benefit of GeoNode is that it can actually serve the geospatial data in its native form in a mapping platform, whereas CCAN is basically a document store. And other examples of useful projects getting everything online for this step one, the Flood Risk Information Portal and data.gov.au are two others that are good examples of how this works. Now, actually, before I move into step two, let's just return to our model simulation. Okay, so all our model runs have completed now. Let's look at the results of this is our first situation where the extension has covered across the floodplain, and there you can see there's a large amount of ponding at the back of that extension, and it's impacting these three houses upstream, which, look, they're not going to be very happy about that, and I don't think that's appropriate development to be going on in the floodplain. So we might be tempted to sit here and try and visually compare these two results by flicking one on and having a look at the other one, flicking one on, having a look at the other. But one of the benefits of running this stuff online is when we have those consistent processes that we know engineers and planners are doing the same thing time and time again across project after project. We can build tooling to effectively build use case specific tools to solve these problems based on the user experience and the user story. So in this case, I'm going to compare the 100-year run with the proposed situation. And what this tool will do is effectively subtract the different water surfaces and map out the difference of them, so we can really isolate the impact of that development proposal that we just saw. Now, while that's calculating, I'll flick back. So what we're really doing here is taking that next step from just having a common data environment, which essentially just stores the data online. We're adding this compute facility onto it and giving, through the user interface, giving the user access to actually compute the data off the database. Aside from being super convenient, this is essentially removing the need for any of these collaborators, these stakeholders, to store the data on their laptop or in their corporate network or hidden away behind wherever it needs to be. That doesn't mean that you can't store that data there, of course. Because we're using open source and open data technology, everything here can be downloaded and can be stored on your network. There's always a need for that. But the point is, everyone else who's collaborating with you on the project, from your developers to your oversight agencies to various stakeholders during an EIS process, for example, are all using the same data and it's up to date. And of course, when we're building compute things into this, it also opens the door for us to incorporate other live data sources that you couldn't incorporate traditionally into a PDF or a static flood study. It enables us to bring in data from IoT sensors throughout a watershed, and it enables us, for example, to bring in radar data from the Bureau of Meteorology and run these models in real time to inform emergency management decisions. And then as more industries and more disciplines move to this kind of workflow, you can see an environment where the predictive flood modeling can incorporate with the predictive traffic modeling and help manage evacuation and these kind of interdisciplinary challenges that can really improve the resilience of our cities through technology. Essentially, from the technical side, what we need to do this, we're adding versioning and history and data management tools so we can handle the change, and we're adding compute power. These are the ingredients that you really need to take this second step. So I'm going to flick back to our scenario. Now, I just need to refresh the browser here. My poor VPN is getting jammed up with both telecasting this thing and downloading all the data. Okay, so now we should have a comparison between that base scenario and our proposal now. I'll turn on the proposed structures there so you can see. So here we've effectively got a map very quickly and very easily that can show us what the challenge is. And you can see here the exact extents, and we've really isolated the impact of this particular change that we made to the model. And you can see the buildings that it's impacting on, and this is the kind of thing that will help you design the mitigation measures that enable responsible and long-term environmental management of the flood challenges within a catchment. Now, I think at that point, I've covered everything I needed to say. I'm just going through my quick mental checklist. There was one other thing for the modelers in the room. I just wanted to show you. I know there's a lot of separation between what you'd normally do in code and what you'd normally do if you're running this kind of model on your desktop. But we can bring all that data out through the web interface too from the modeling side. So this is the technical report of the actual model log run. That's all available to you. And it's probably a concept for a different talk, but for the modelers in the room, we can run through the actual model structure and setup and how you would go about taking this sort of thing and checking it and running it on your desktop so that you're not dependent on having an internet connection. You're not necessarily dependent on using this methodology. You can still do it and interface it with the old way. And I expect for this kind of thing, you're looking at a hybrid transition where you slowly and incrementally move from doing things the way you're currently doing them onto this kind of strategy in small steps, testing each step along the way that the business process is applicable and the data management is actually serving the purpose that you're looking for. So in terms of implementing this kind of digital transformation, the recommendation is to do it piecemeal and step by step rather than launching into one large big change that's going to create the business process challenges. So in summary, I'd like to say that, yeah, the technology exists. Everything here has been built using open source tooling, which means from a licensing point of view, your challenges aren't that challenging. But the business process part of each user needs to evolve along with the technology. And this is the part where you really need to consider how this will fit into your business processes and who your users are and what value you're trying to provide to them as an organization. And based on that, then step into using these tools to provide that value that you really want to give to your customers and to your stakeholders. So at that point, I'll flick over. Oh yeah, the code is available on GitHub. Talk to me and I'll talk you through it if you're interested in understanding and using or replicating any of this. And at that point, I'll flick open to questions. If I can get you guys back up on the screen.
Thank you very much for that. Thanks, Sam. It's a two-part question.
Sure.
The first one is, do you think it's possible, or are you already doing it, where you can have simultaneous input from a hydrograph and a radiograph, by interrogating each time step, have my inputs changed, retain the time step you're at. For instance, I'll put it in an example form. Say you begin a storm with a predicted hydrograph.
Yep.
Getting real-time input from sensors, those predictions change 5 minutes into the storm, then you will say, all right, retain the 5-minute time step that we're at, but insert the new radiograph and hydrograph.
Right. So you're asking about updating the rainfall as it comes from the gauge during a model run.
During a run.
Yep. The answer is yes. Because I think it would be, everything here is built on Python, and there are a number of Python libraries that could handle ingesting that data from the rain gauge. You'd have to place it in a staging area and then just address the code for the model to make sure it's reading the staging area dynamically, which isn't too hard. So yes, technically that's possible.
Which is how conceivable do you think it would be to have a system, an architecture model, where rather than a centralized model running that distributes outputs to devices, you have devices on blocks which is specific to a purpose. A couple of examples of this would be if you have an emergency response agency that has a localized, very fine resolution, but small extent model running on their phone, but every time step it interrogates a cloud data source or has the hydrograph or radiograph update or need to change my inputs, but the actual processing to do the model is done on the device. Or you can have it for a station that needs inputs. It needs inputs from a larger hydrodynamic model in order to figure out what data to capture, like the system that monitors the hydraulic effect of every blockage on a culvert. It needs to extract the effect of the culvert itself. Now it needs hydraulic conditions, get those from the parent model, but the fine scale model, run that on the local device.
Yeah, okay. I understand it. It's a cool question. I guess my answer would be that from an architecture point of view, sure, you can ship the results of a real-time hydrodynamic model at a certain interval to the edge devices, and there's no reason they can't calculate the results on the edge like that. And feedback. I like the idea of feeding back real-time blockage on a culvert, for example, using some kind of IoT sensor. That I hadn't thought of that, and that's really cool, because it would have a really direct benefit to how emergency managers would deal with a storm, for example, if they know that a certain culvert is blocked during the event and they know what the impact of that blockage is going to be. You can get guys to go out there and undo the blockage before it causes damage. From the water engineering side, from my hydraulic engineering, I'd be nervous about whether you could calibrate a model to a level of resolution that I would trust that real-time input is going to give you data that you can trust as an output. You'd need to calibrate your model to handle that specific input from the edge. And because kind of by definition, you don't know what that input's going to be. And for example, with blockage, that'll be a really, like a mattress is going to behave very differently to a log. Trying to get real-time hydraulic model results out of that might be a bit more challenging. To actually make that happen today, I think you'd need a lot more research in how that calculation actually works. So from an architecture point of view, I think yes. From a hydraulic engineer point of view, I think you've got to be careful about effectively overfitting and overvaluing what the hydraulic model is capable of. I think in that example, it might be better just to send the guys out and have a look.
Yeah, we've got similar reservations. What we're actually thinking about doing is a learning model that does stuff like develop what the effective, simultaneously get better at modelling the hydrodynamic response to the caching, but the effective debris build up a database over time.
Yep.
So that we have something, we have a curve that we can interrogate from the debris pattern rather than just saying that we're going to have a stab in the dark.
Yeah. Exactly. I think you need a long-term project with heaps of data to start building that machine learning model, which of course is possible, right? If you do a long-term project and you get lots of data. If we tried to implement it based on the data that we have tomorrow, I'm not sure we'd have enough, but if you can set up the sensors and collect that data, that would be super valuable for flood management everywhere. If you can figure that out, yes.
Thanks, Dave.
Hey, David, it's Isabel Gates from the podcast.
Hi, Isabel.
I particularly liked your presentation and like the concept of evolving model and always current models. One of your final words were about the technology is there, as you demonstrated, but they need to align with business process. As you know, in the South Wales and generally in Australia, we are governed by, and especially working for local government, we are governed by government processes. So I was interested to hear whether you have an approach or you have the opportunity to present some of the concepts of represented today to government, or if you have implemented any of these concepts for government.
No, one of my challenges of living here in Dubai is that I haven't had much of an opportunity to get face-to-face with government. I did talk about, I've been here for about 3 years now. I did talk to Department of Planning about 4 years ago about these concepts. And they were well received at that time, but the tyranny of distance means I haven't been able to drive this home in New South Wales. But a lot of the work that we've been doing has been in jurisdictions where the business process isn't so much of a challenge compared to the burning need to solve the physical problems. I've been working a lot in Nicaragua, in India, and in the Midwest United States with these kind of methodologies, where we haven't had to worry so much about the business process because people just actually want to solve the problem and don't have the same constraints. So my advice would be to, what we've learned from actually doing it is to take small steps and prove the value at each way of the change. I don't think the right approach is to necessarily change all the regulation immediately. And I think the first step is to start demonstrating the value within the bounds of the existing regulation structure, and then use that value from the actual results of real-world development application assessments, for example, to then use that as evidence of why the regulation should adapt or evolve to handle this. I don't think it's going to be a wise or successful move to try and change the regulation prior to having the demonstrated evidence that this new process works in this specific environment. Does that make sense? Hi, Ricardo.
With these methods, you actually point out at the beginning of this presentation that you would rather be here face-to-face talking to us.
Yep.
Do you find that anything with those collaborative methods, using the web and the cloud, do we lose anything with this face-to-face interaction?
You can never replace the face-to-face. You always need to do that. The challenge that I had when working as an engineering consultant with face-to-face, at the start of a project, we'd go around and we'd meet all the stakeholders and we'd establish a rapport and we'd know who we are. This helps with phone calls throughout the rest of the project. But as the projects go on and get more complicated and you have more stakeholders and more data flying around, the digital collaboration becomes really useful to scale the amount of information transfer between people. But if you don't have that initial understanding of what you're trying to achieve as stakeholders, and you don't have that trust in all the benefits that you get from face-to-face collaboration, that's something that technology can't replace. But where the technology can influence things is once you have that framework for collaboration and you have that understanding between two humans, you can really scale and accelerate the information transfer. And that means you're not getting in the car and having to go and redo your presentation every 2 weeks, every time your design changes.
Just continue on that. You showed us one of your tools. I believe that your system, your process of design collaboration, you have more than that, perhaps. And does this system have a way to capture the decisions and the discussions that happen over those tools and maps that you have to demonstrate?
It's an interesting question and one that we've been exploring. You can certainly, while I answer this, I'm going to bring up an example here. Let me just reshare my screen again. So one of the projects we did in Chennai was to actually digitize the whole flood study. So here we've got both the text of the flood study, and inside it we have dynamic updatable figures. So you can picture this kind of web page as a PDF report that you can query and update and interrogate. So this kind of technology could be used to capture the decision-making behind a particular set of decisions and a set of model runs, and presented in the same way. And for example, this particular page is editable through the browser as well. So I can update the text in here once I sign in. I won't go through that whole process. But this is updatable similar to a wiki page. So anyone as part of the project, if they have the login details and the right credentials can update the text and see how this is being presented. So that's one example of how you might go about capturing that use case specific textual data around it, around this kind of thing.
Dave, I was just going to add a comment to that. You could easily link like a Jupyter notepad to it to make the whole thing much more interactive, so that you could track, you can actually track your model builds within the document within a Jupyter notepad. That
Yep.
Within that structure of that document you just showed, you've actually got the capability of doing it run.
Yeah. Exactly. So currently currently you can do that using GitHub. So if you wanted to change the actual code of the Anuga model, and this would apply for any script that you're using, you can simply commit to this file, and that'll update your run directly if you have the right server configured and all that sort of thing. So yeah, it would not be a stretch to, instead of just doing it through GitHub, you could do it like Stephen Roberts has done with at ANU with his as we were discussing earlier with the Cloud9 code editor through the web. You could do the same thing to make the modeler's life really easy in terms of getting into the back end and coding the Python for each specific model run. So yeah, certainly that stuff's all there. It kind of works that way in the back end, but I haven't built the user interface to make it all pretty for the modelers yet, because they tend to be more tolerant of working with non-UI tools. But certainly it's there.
Okay, thank you very much, David. For lack of time, we could stop here. I would like to thank you, and then I would like to thank David for this great presentation.
Thank you so much, everyone. All right, see ya.